Brilliant. We shall start. Right. Well, welcome all. Thank you for coming along. This is a talk by Professor Mike Zaworotko. I can't pronounce your second name. Zaworotko, or whatever. We'll pass that on crystal engineering. I'm Mike Bloomfield. I'm the secretary of the Southeast region of the analytical community, and yeah, and this is the first time that we've actually held a physical and an online event. So I hope it goes well, particularly the online bit. It's organised jointly, well, it's organised with CERAC, as we call ourselves, with the Kent and the Bristol and West local sections. So thank you to them for joining us on this event. Interestingly as well, there's more than 100 people attending online. So I haven't counted the amount of people here, but it is quite a large event. It will be recorded, so there'll be people watching afterwards as well. The talk should last for approximately 45 minutes, with 10 to 15 minutes afterwards for questions. Online, can everybody please ask questions at the end of the event? And online questions will be collated by Steve Barton, our treasurer, who will collect the questions and read them out at the end. I think that's it. Also, our chairperson, Joanne Elliott, you've met, she checks you in. Right, important stuff for people here. The toilets are located downstairs. You go downstairs, turn left along the corridor, and then on the left-hand side, that's the toilets. There's no fire, there's no fire alarm intended for today. So if it goes off, it's genuine. If the fire alarm goes off, we all exit through the main entrance into the courtyard or through the Geographical Society and out onto the pavement. So that's the online bit. That's the physical bit. More interestingly now, Professor Mike Z is an old friend of mine from our university days at Imperial College. And when we studied there, a professor from the University of Alabama came across to visit the college, and Mike was brave in the fact that he went back with this professor to do a studentship PhD in Alabama. And I personally had I couldn't do that. I wasn't brave enough for that. So Mike got his PhD in Alabama. He then went on to the University of St Mary's in Nova Scotia, and then on to the University of Winnipeg. Bit chilly, but he finished off after that by going to the University of Southern Florida, nice and warm. After that, though, he was appointed the Bernal Professor of Crystal Engineering at the University of Limerick, where he still is now. So that's enough from me. Without further ado, over to Mike Z.
Thank you so much, Mike. And actually, it was the Bunch of Grapes, was the pub that sealed my fate to go to the US when I was 21 years of age. So it's a real pleasure to be back here. It's been about 6 years since I last presented. By the way, I love to walk around, but since it's being recorded, I suppose I better stay by the microphone so you're safe. I'm not going to get too close to the audience. And a lot has happened in the past 6 years. So when I came here before, I had a similar message that it's time to do things differently. It's time to do things sustainably. Well, a lot has happened, both good and bad, since then. And so at the beginning of my talk, I'm going to talk about the background to all of this. Also, you won't know it, Mike might remember, but from my voice and from my name, you won't tell that I was born and raised in Wales. So that means I'm naturally inclined to exaggerate in a not very convincing manner. So maybe I should change the title of my talk, Why They Could Save the World. And also, as you'll find out in a minute, you'll be giving me a new name, which is Dr. Doom, because I think it's now urgent that we address the need to become sustainable. So I will do that first, a bit of history and a little bit of geography that goes on it. Then I'll have two main themes, molecular solids and how we can now control solubility at will and why that's important for pharmaceuticals and any medicinal compounds for that matter. Then I'll talk about coordination networks, which is a class of material that didn't exist when I was a student and didn't even exist until the 1990s, and how by a process called pore engineering, we can create new materials with properties that far exceed anything that came before at a time when we desperately need them. And then I'll just have some brief conclusions. A little bit about where I'm from. Today was Nobel Chemistry Day. If there's a person who ever deserved it and didn't get it, it's this guy, J.D. Bennell, who was born and raised near Limerick. I'm the Bennell Chair of Crystal Engineering. We have a Bennell Institute named after him, and that's because he was a pioneer in the field of crystallography, in particular as it applied to structural chemistry and biology. And he's known for two early discoveries. One was determining the crystal structure of graphite, and then in 1934, he published the first ever diffraction pattern of a protein. So he was the person who started structural biology. And he also trained students in structural biology. That included two of his students who won Nobel Prizes, Dorothy Hodgkin and Max Perutz. By the way, he didn't put his name on his students' papers, but he did publish these two seminal papers. Perutz was the mentor of Francis Crick, who came up with DNA. And so he's directly responsible through his chemical children for 3 Nobel laureates. But he was a true polymath because not only did he work in chemistry and biology, he also recognized CO2 and climate change in the 1950s and was credited with the idea of the Cambridge Structural Database, which is the first scientific database, the forerunner to what we now call AI through database mining. But, as I said, a lot of things have happened over the past few years. And when it comes to climate, they're bad. And by the way, I want to make a big plug for the RSC. I love the RSC anyway. But when they do online events like this, you don't know who's going to look at it at some point in the future and hopefully be positively affected by it. So it's good that these are available. And in fact, I received an email just under a year ago from a person who had viewed a previous RSC event that I was involved in related to one of the COP conferences when we talked about porous materials for addressing global challenges. But the email said in a very few words what I would say in 45 minutes. So I'm going to repeat what was in the email. So much of what I see in the news and popular media seems to me to be underwhelming, whether it be electric cars or solar panels on houses. I need to find something that will give me a shred of hope for the future. I totally agree. Electric cars and solar panels are not going to save us from climate change. And then he said, today I discovered this thing called metal organic frameworks. So I'll tell you a little bit about metal organic frameworks and how we got there. But first, this business of what's going on with the climate. I became interested in research related to climate change when I visited a very special part of the world. And as a clue, there are penguins down on those beaches, so it's nowhere in the northern hemisphere. This is the Cape of Good Hope in South Africa. And there's a little hut at the end of the Cape of Good Hope where they measure CO2 levels. So the first time I'd seen one of these curves was when I visited one of the sites in the world, there were only a handful at the time, where they measure CO2 levels. And I thought to myself, well, we got to do something, but hey, we've got a long time to figure this out, right? But I became interested in CO2 capture at that point as a sideline to what I was doing in research. Well, if we fast forward just 15 years later and look at the curve, it sort of looks the same, but I think it's pretty obvious that it's increasing. The rate of increase of CO2 is increasing. And in fact, if you dig down into the data, in the 60s, it was 1 ppm per year. In the 90s, 1.5. In the 2010 era, it was 2 ppm. And now it's 3 ppm. And I'm not doing my Welsh stuff. I'm not exaggerating. In the last year, it's gone up 3.44 in 1 year. So this is actually an exponential increase in the rate of increase of CO2 levels in our atmosphere. So clearly we have a bit of a problem here. And the reason, I hate to say it, it's crystal clear. Fossil fuel emissions are responsible for 70% of anthropogenic CO2. So there's another 30% on top of that. But they're not going down. We're not reducing fossil fuel emissions. They're continuing to go up. They're a smaller share of global energy production, but they're not going down. And 2023 is where things went out of control in several ways. The obvious one was global temperatures. So what happened in 2023 is that we set a new record for global average temperature, but it wasn't slightly above what was there before. It was the biggest jump ever seen in the record global temperature. It went up about 0.35 degrees Celsius in 1 year. In 2024, the trend continued. In fact, July the 23rd, 2024 is the hottest day ever recorded on the planet. If you look at the rolling 12-month temperatures, anybody who says it's a blip is not looking at the data, right? The data is self-explanatory. The world has already increased in temperature by 1.5 degrees on average since around 1980. And this is not my data, this is publicly available. And last year was not just the trend, it was above the trend. And what happened last year? Well, northern Canada had forest fires, Hawaii had a raging inferno, and today West Florida is going to get hit by a hurricane coming from a direction that hasn't happened in 150 years. So clearly there are things going on. In Europe, it's even worse. If you look at Europe and look at the fine print, it's actually Europe has increased by 3 degrees since 1980. And it's not uniform. So all those people who think, well, it'll be okay in the UK and Ireland, we'll grow red grapes and we'll be going to our vineyards and enjoying wine like Italy and Spain. No. The UK and Ireland are actually cooler over the past 40 years. But Southern Europe has increased in temperature. So if you do even the simple math, well, if it's on average 3 degrees and the northern part is the same, then it's 6 degrees warmer in Southern Europe. And anybody who's been to Italy recently in August knows it's no longer comfortable to be out and about during the day. In fact, I was there a few weeks ago. It was 36 Celsius. I'm like, surely this is normal in northern Italy. And I looked it up. The normal temperature was 26, 27. But it's consistently now mid-30s for months in the summer. So it's already happened. And I did a little bit of homework. UN SDG 13, which is the one that addresses climate change, used to say we will reduce CO2 emissions 50% by 2030. I went to the website yesterday and they don't talk about that anymore because it hasn't happened, as I showed earlier. So the plan was that by 2030, we'd be down here and we would save the world from 1.5 degrees, or up here and save the world from 2 degrees. But does anybody really think that's going to happen, right? I don't think so. Everything is out of control. So I underwent a phase change last year. Instead of going to work, because I loved what I did and I was curious and I loved working with students, I'm now worried about my future, never mind my children and grandchildren's future. It's absolutely essential that we collectively do something about it. And chemistry caused the problem, and chemistry can offer the solution. And what is that solution? It's better, cheaper, greener materials to address global challenges. They're not solvable at the moment because we don't have the right materials that have the functionality at the cost to enable us to do things like improve medicines to make them better and cheaper, better and more efficient solar energy harvesting materials, access to clean, pure water everywhere on the planet, and of course CO2 and other pollutants that are in air. We need to remediate them. So that's really the message I've got. If you take one message home, it's that we urgently need better, cheaper, greener materials, and of course we need more money to do research on them, but that's a separate issue. And that brings me to crystals. So I love the RSC. I definitely love crystals. All crystals, who doesn't? What is a crystal? It's a funny question because everybody knows what a crystal looks like, but what is the definition of a crystal? And sometimes you'll get like a 5-minute answer from people, but it's a very simple answer. It's a repeating pattern of atoms, molecules, or ions in 3 dimensions, and you can add with long-range order to that. So it's over a long range. It's not over 20 molecules. It's over thousands, tens of thousands, hundreds of thousands of molecules. And they're all over the place. They're hugely valuable, but I don't love them all equally. Diamonds, they've cost me a lot in my lifetime, and they're not going to save the world. The other 2 types of crystals that I have here can, and these are actually prize-winning photos of a pharmaceutical crystal and of a metal organic framework material. This was my student. This was a member of our institute. And so I love those 2 types of crystals. But all crystals have the same basic properties, which makes them special. That is that they're relatively stable compared to all other options for a solid. They have high purity. In fact, we use crystals to purify substances. They're consistent and reproducible in terms of their properties, which is hugely important in pharmaceuticals. They can be processed. You can make a gram or a ton of crystals at a time. And some crystals can have the property of porosity, which can be very special in terms of separations, sensing, conversion of everyday chemicals, including commodities. But there was one problem. This was the state of the art throughout most of history, most of modern chemical history. You can't design a crystal the way you can design a molecule. Chemists learned how to design molecules an awfully long time ago. Many of the basic rules of synthetic chemistry were available 100 years ago. Crystals, no, they are what they are. Just like all materials, they shake and bake. A crystal is what it wants to be, and we can't do anything about it. But the dream of crystal engineering, which is the field of chemistry that studies the design, properties, and applications of crystals, was well expressed by Richard Feynman, a Nobel laureate who is credited with the dawn of nanotechnology and nanoscience. He asked this question in his series of lectures: what would the properties of materials be if we could really arrange the atoms the way we want them? And he had a very profound answer, especially over here. When we can get control structure, we can control properties, and we can do different things that we can't do at the moment. We can essentially improve the performance of materials by design. And pictures can speak louder than words. M.C. Escher is famous for his drawings, providing three-dimensional depth and symmetry. So you'll find his diagrams in crystallography labs all over the world. These are actually could be used as blueprints to design crystals, if you could do the chemistry properly. And the one on the left is obviously a porous crystal. To be specific, it's a primitive cubic crystal, or PCU. We love three-letter codes in our field. And you can see there's empty space. So it's like molecular Lego. On the right, we have a polar molecule all aligned in the same direction in a crystal, which can lead to very interesting properties. And it's something that we want to do, but we can't control. And so this, for example, could be a molecular crystal such as a drug molecule. Now to the past. So this is 1977, the year I graduated from Imperial College, and I went to the Bunch of Grapes and had a few beers and signed on the dotted line without knowing what I was getting into. One of the reasons I mentioned this, it emphasizes how time has changed, but also how we can go back to the past and learn things from the past. So who all is in this picture? Well, it's the whole crew from our year. And one thing that was very different, there was only one female professor and 6 female students. This is 20 plus male professors and 67 male students. It was actually hard to spot them in these grainy photos because everybody had the same length of hair, right? I still do. I'm a little bit more groomed than I used to be. But also in this picture are 2 very influential people, Geoffrey Wilkinson and Richard Barra. Geoffrey Wilkinson won the Nobel Prize in 1973 for organometallic chemistry, and organometallic chemistry was going to save the world. And I got excited by organometallic chemistry, and that's what I went to do as a PhD student. Richard Barra was the father of synthetic zeolite chemistry, and he changed industry and should have won a Nobel Prize. Another should have won a Nobel Prize person who didn't. I'm going to mention Barra at the end because he did some work in the late 60s, which we are resurrecting, and the results are much far exceeding our hopes and expectations. That's Mike B. That's Mike Z. In the crowd there, as I say, everybody seemed to have the same length there. There was not much work for barbers back in those days. So what happened over the next 20 years is basically nothing. This was after I graduated. There was no progress in the design of crystalline solids. And then in 1988, John Maddox, who was the editor of Nature at the time, wrote an editorial calling it a scandal that in the physical sciences, it's in general impossible to predict the structure of even the simplest solids from a knowledge of their chemical composition. Now, I'm a bit retentive about literature. Normally, I'm not retentive on the date, but this was published on the 15th of September, 1988, and that was when I said, I'm going to study crystal engineering. What a challenge, right? Who cares what we can do? It's a scientific challenge of the grandest order. It's also, because crystals can't be predicted, means that if you make a new crystal, you can get a patent because it's unexpected and in many cases regarded as inventive. So I will just say it's used as justification for patenting crystal forms of drug substances. I'm not going to say if I agree that should be the case. It's just the reality of the situation. Then what happened 9 days later in JACS, not an RSC journal, unfortunately, but a very well-known chemistry journal, a paper was published by Otto Irmer 9 days later, which showed a crystal structure that was predicted from first principles by knowing the molecular structure. And in this case, he made a molecule, adamantane tetracarboxylic acid, which self-assembled by the expected carboxylic acid hydrogen-bonded dimers to build a three-dimensional structure that was entirely predictable. And what is this structure? Well, that's an adamantoid cage, and the full structure is diamondoid. It's like diamond, because it's tetrahedral building blocks that self-assemble in 3 dimensions. And so this was, I would call crystal engineering 101. The same thing can be done with metals. If you choose the right ingredients, you can predict the outcome. And a year later, also in JAX, Bernard Hoskins and Richard Robeson from Australia reported what would be called today a MARF, the first MARF. It was a coordination network, once again because of the self-assembly of 2 tetrahedra, inevitably was a diamondoid or diamond-like structure, which we abbreviate to DIA as a 3-letter code. Robeson in 1990 published a paper which didn't really have the same impact, but was more important. And because he showed that you didn't just have to have a tetrahedron to build a tetrahedral structure or a predictable structure, that you could mix and match. You could do a kind of modular self-assembly where you have nodes and linkers, and demonstrated it with a 2-dimensional net. It's a square lattice, or SQL, as an abbreviation. And the chemistry here is known chemistry, but the outcome is profound because it's a predictable structure with predictable dimensions and a predictable property. And so this approach is to take a metal or a molecule, which can be a node. Node means 3 or more connections. In this case, it's 4. It's an octahedral metal with 4 ligands bonded to the equatorial plane. This is a Werner complex that were reported by Werner in the 1930s that started coordination chemistry. What they did, though, was instead of just hoping it would somehow assemble into the right structure, they forced it to, with a linear molecule which only connected 2 points, and that's what we call a linker. So node and linker inevitably produce empty space, and that empty space means you've got a porous material, and you've forced the issue. So the rest of the story is that a lot of people thought MARFs would get the Nobel Prize today because it's been such a high impact area of chemistry, but it hasn't happened yet. Many nodes and many linkers. There are more than 125,000 of these network structures. They're highly modular, so you can mix and match the metals, the building blocks, and sometimes you can have multiple building blocks and metals in the same structure. So it's a whole new field of materials chemistry, but at this point, it's still design. But these are the basic design principles. In 1997, the first 2 permanently porous materials were reported. They're both 2-dimensional structures. They both came from Japan. One was in Angeventer chemie, the other in chem letters. And one of them involved 4,4' bipyridine, the same ligand as before. The other, the carboxylate analog, 1,4-benzene dicarboxylate, or terephthalic acid. So far we've made a not as good, not as stable, more expensive zeolite. Who cares, right? But then 2 years later, everything changed. And that was when the first materials that do something different, that exceeded anything that came before, were reported. The first was HCUST1, which was reported in Science in 1999. It had a surface area of 1,900 meters squared per gram, which is 1 soccer field per gram of material. Soccer, is that what you call it? Football. Football over here, which set a new world record. 6 months later, another new world record, but by a big jump to 3,000 meters squared per gram. So suddenly we had learned how to design materials, and now we had ourselves properties that far exceeded what came before. Also in the terms of the development stage, molecular compounds can also now be designed to have a certain composition and structure. And this was work that I did on co-crystals, asking whether a carboxylic acid would rather bond to itself or to an amide or a pyridine. The vernacular is that this is a supramolecular homosynthon to identical complementary groups that come together. This is a supramolecular heterosynthon, which is two complementary but different groups that come together. And there were examples of these, but there was no statistics, there was no design. And what happened is that by a combination of statistics and experiments, we were able to show that reliably this happens and reliably this happens, that the heterosynthon dominates over the homosynthon, even though the homosynthon is well known since the beginning of supramolecular chemistry. So this is basically the key to co-crystal design. If you have a molecule with a carboxylic acid and a molecule with a pyridine or an amide, you're off to the races. So this was around 2002. So what happened from that discovery is that the field took off very quickly. So I'm calling this now graduate school crystal engineering, because now we're actually doing things that are relevant to the outside world. Co-crystals were long known, but they were understudied and little understood. And in terms of long known, I mean really long known. Molecular crystals go back to at least 1841. If you're an organic chemist, you know what quinhydrone is. It's a reagent. It's actually a co-crystal of paraquinol and paraquinone. So it's the prototypal molecular co-crystal, also an Escher diagram showing two different molecules or entities packing together. There's also a class of co-crystals called ionic co-crystals, where you take a salt and a molecule, or two salts, and make a co-crystal. These date to at least 1783, when sodium chloride and urea were crystallized, and followed up in the about 50 years later by sodium chloride and glucose and sodium chloride and sucrose. At that time, all anybody knew is that the crystals had different properties and different morphology, but they had fundamentally very different composition as well. So in 2003, 2004, the first papers on pharmaceutical co-crystals by design were published. There were 4. I published 2 of them. Other groups published the other 2. And they took pharmaceutical compounds and made co-crystals and studied structure and properties. All 4 of these papers, by the way, have the same first 2 words in the title, crystal engineering. These were planned experiments and planned outcomes that were successful. So what's happened to co-crystals since? There were no pharmaceutical co-crystals before around 2003, 2004. But interest in both design of co-crystals in general, the dark blue, and reports on pharmaceutical co-crystals in particular have dramatically increased since 2003, 2004, now to where there's more than 1 a day. And they all go back to this work in 2003, 2004, and I've highlighted this one molecule, carbamazepine, which is kind of the poster child for problem molecules in the pharmaceutical industry, because it forms multiple polymorph solvates and hydrates, and it's hard to control. So what happened, a former colleague of mine, Jonathan Steed, who is now the editor of Crystal Growth and Design, published a paper just a few months ago on what's happened to carbamazepine since the co-crystal papers were reported. And this graph speaks a lot. All of the work that was done on carbamazepine until around 2003 produced 10 crystal forms, solvates, hydrates, and polymorphs. Once co-crystals came along, there was not a steady drip, there was a fire hydrant torrent of new phases of co-crystals. So now we have 150 new crystal forms of carbamazepine. If it were only new forms, it wouldn't be such a big deal. But as I'll explain in a moment, there's also the matter of the properties. And the properties of a pharmaceutical solid are critically impacted by its solubility and dissolution rate. And this reference is from 1897, by the way. There's no typo there. This is 1897. The Noyes-Whitney equation on dissolution of solids was published in 1897. And what it said is that the rate at which a solid substance dissolves in its own solution is proportional to the difference between the concentration of that solution and the concentration of the saturated solution. In other words, it's not the molecule that has a solubility and a dissolution rate, it's the solid form of that molecule. So solubility is not a molecular property, it's a solid property. And different solids will have different solubilities. And that's important because so many of the new chemical entities being developed, small molecules by pharma, which still represent around 50% of the new drugs introduced and are likely to continue that way, have a solubility problem. So if you can make a solid form that has better solubility, you can turn something that will not be biologically available into something that is. And another side to this is that polymorphs and solvates and hydrates do not change appreciably the solubility of a compound and hence its dissolution rate for a very simple reason. They have very similar lattice energy and therefore solubility. And this isn't my work again. This is a survey of polymorphic pairs of drug molecules. And what you find is that majority of them have the same solubility to all practical intents and purposes. There are only a few outliers, and the outliers are the exception that proves the rule, right? Most of the time, you don't solve any problems with polymorphs. And even here, the outliers, ritonavir and chloramphenicol palmitate, are only 4 times more soluble than the other polymorph. Polymorphs are not a solution. In fact, they're a problem. Co-crystals, though, are a solution because you can have 1,000 times more soluble or 1,000 times less. And the roadblock was really that they were new and the regulatory bodies didn't know what to do with them. But by the mid-2010s, both the European Medicines Agency and the US FDA had issued guidances basically giving a green light to pharmaceutical co-crystals as drug substances. And since then, we've ended up with around about 10 new drugs that are pharmaceutical co-crystals, and 2 of them are blockbusters. Entresto and Biktarvy are based upon co-crystals, and they're billion-plus-a-year revenue drugs. So where do we go next? Well, in my group, we've really focused on these ionic co-crystals because you've got 2 variables. So you can have even more solid forms of a compound. And those would include phosphoric acid phosphate co-crystals, azole-azolium co-crystals, and phenol-phenolate co-crystals. And between these functional groups, you can cover almost every drug molecule that's out there. And those are my students, Molly, Mariam, and Shasha, who worked on these areas. So let's move to porous materials. Crystal engineering has come a long way, as I mentioned. Coordination networks, in order to improve the properties, you need to be able to control the pore. But in what way? We'll find out in a moment, because this is where modeling provided absolutely critical insight that now looks obvious, but wasn't obvious at the time. Now, if you remember a few minutes ago, I said we're making bigger and bigger pores and more surface area. We're going to set world records. But what are you going to do with empty space? Empty space has no properties, right, to speak of. And so it now looks obvious, but we did this in computero experiment. Brian Space and Tony Pham, his student, who had to evacuate his home yesterday because it's in St. Petersburg, Florida, studied this gas phase hypothetical structure of 4 benzene molecules and a hydrogen molecule. At the time, we had funding to do hydrogen storage, and we were interested in what kind of pore size and pore chemistry would improve the binding of the molecule to the pore walls. And the calculations came out, and of course, if you do a calculation, you'll get a result. And they disagreed with each other in terms of the absolute energies, which they will always do. But they all agreed on one thing, which is that the strongest binding will be at the van der Waals surface of the molecule that you're trying to attract. And not only do they tell you that, but they tell you it's actually a very narrow window. At half an angstrom, it's too far. You've got to be bang on the van der Waals surface to get very tight binding between hydrogen and aromatics. So if you take that principle to its natural level, well, small molecules, you need small pores. You don't need big pores. You need small pores. So the message from this was pore size really, really matters, and I'm understating it again. Since then, we've published 50 or so papers, which means I'm a person of ordinary skill on modeling. I know how to ask questions. And Brian had to develop new potential functions to better explain the results we were getting. Because we also discovered, because we're crystal engineers, how to control pore chemistry. And pore chemistry can be inorganic or organic, or a mix of inorganic and organic. And a good example would be these PCU nets that I showed you earlier, that are from the Escher diagram, the primitive cubic. There's a very famous primitive cubic network, and it's called Prussian blue. It's purely inorganic. There's a famous morph called DMorph1, which has a mix, is all organic. It's organic layers and organic pillars. And there's a material that we first reported that we call CIF63 zinc, which has inorganic anions in one direction and organic molecules in the other two. So really, there are 3 distinct classes of porous solid, depending upon whether they're organic or inorganic or some hybrid combination of them. And by the way, I love Prussian blue. I love all these things. Right? I love Prussian blue. It's my favorite painting. The Scream is not my favorite painting, right? I love Starry Night, and the dark blue in Starry Night is Prussian blue. And it's been around 150 years and hasn't gone bad, right? So Prussian blue is a really good material as a pigment. My third most favorite painting, Mona Lisa's number 2, is the Great Wave of Kanagawa or Kanazawa, one or the other, which is in the art museum by the palace in Tokyo. And I've been up and looked at that up close. Guess what? It's got Prussian blue, and it's even older. It's approaching 200 years old. So now we have available a range of materials with small pores that we can control. We're off to the races. So this is Crystal Engineering 601 now. Instead of large pores and large surface area, we actually want to go even smaller than small. We want to go ultra microporous, which means pores less than 0.7 nanometers in size. And when we combine the right chemistry with the right pore size, amazing things can happen. These different things that I alluded to earlier. So in 2013, my undergrad student, Stephen, had the undergrad honors project from heaven because he got a JAX paper and a Nature paper from his undergrad honors thesis, because we took a known compound and we exposed it to CO2, and we found this material just sucks up CO2 at very, very low pressures because it bonds so strongly. But it's still a physosorbent, so you're not chemically bonding it, and you only need mild temperatures and vacuum to release it. So this material, which is CIF63 zinc, set a new world record for binding selectivity for CO2 over nitrogen, which is 2,500. The previous world record was 200. So this was an order of magnitude improvement over anything that came before. And by crystal engineering this material, we went up another order of magnitude. So what does that mean? Well, at least thermodynamically, you can capture CO2 from air. This material will suck up CO2 from the air spontaneously in a way that no other physisorbent had ever done previously before. So, as I said, we were off to the races. We did the same thing for acetylene ethylene. In 2016, we published a science paper where we more than an order of magnitude improved the selectivity, which was over an earlier science paper from a couple of years earlier that had a selectivity of 2. These two molecules are very hard to separate. But we found out a way to separate, and once again, fine-tuning, we now have 2 orders of magnitude improvement in the selectivity. We also did the same thing for ethane over ethene, and most recently, this is the one that's most significant because it goes way beyond even what we saw for the other materials, because it can capture benzene from humid air at 10 ppm levels, even when the air is humid. So all of a sudden now, we have these materials that can be sensors, can be gravimetric sensors, and electronic noses can really work because they can target one molecule in a mixture of molecules. So this opens up a vast opportunity to do very accurate real-time remote sensing using chips that are coated with these materials. And the interesting thing, just as for the first compound, all of these materials were known. Their properties weren't known. They'd been reported, they had been studied, but they hadn't been studied for these particular purposes. So you don't even need to make new materials, right? You can go back and look at these 125,000 MOFs out there and start studying them. I'm going to talk about one of these global challenges now and tangible results that we've had in that area. It's arguable which is the most urgent, right? I would say water. Maybe CO2 is the most important, but water, there's no plan B, and a few days and you're dead, right? If you're out of water. And water is a gigantic problem that's deteriorating in terms of access of humanity to fresh water. This was published in 2016. A lot of people use this plot. Anything that's not green has water scarcity at some point of the year. And the dark reds, it's pretty much year-round. So these are the parts of the world where there's water scarcity. Population is growing, climate is changing, it's getting worse. Just this year, so that's scarcity, there was a report on water quality. And this is a projection of what's going to happen to water quality over the next generation. And if I flip back, wait a minute, all those green areas are purple. So we're facing a point where the whole of the planet is either going to have water scarcity or water quality problems. And it ain't cheap to clean up water. So it would be nice to think we could cut our usage in some way, although I don't know how you do that. For one thing, I'm not giving up my beer. I don't know about you. I mean, beer is not going to go away. But only 8% of all the water in the world is used for domestic purposes. Agriculture and industry use the rest. And we can't do without agriculture when population is increasing. So we're facing an issue where we need a new approach. And the new approach that's really just happening, is developing right now, is called atmospheric water harvesting, or AWH, yet another 3-letter acronym. And it has been traditionally an untapped resource. Now, by the way, if you go to Google and look up AWH machine, you can buy one from China. But I got news for you, they don't work. Because they only work when it's humid. They don't work when it's dry, which is when you actually need it to work. And that's because traditional sorbents and traditional condensation processes only work at high humidity. Anyway, atmospheric water is only 0.04% of water, but that's still plenty of water to satisfy the world's needs. And the beauty of it, it's completely renewable. If you evaporate water, if you capture water from the air, it will evaporate from lakes, rivers, and the ocean as water, not as salt water. And there already are materials that are brilliant at capturing water from the air. These are the zeolites that I mentioned earlier. They're called desiccants. They're used as desiccants. You've seen them. Silica gel and zeolites are used as desiccants. But there's only one problem. They capture the water so well they don't want to release it. So you have to use a lot of energy to get that water back out. So what we're facing is we need a new class of material, a new class of desiccant, which is optimized for absorption harvesting, atmospheric water harvesting. So we call them regeneration optimized sorbents, or ROS materials. And a ROS material must be low recycling energy, so you don't need much energy or much stimulus to recover the water. They've got to be fast, so you can get high productivity per kilogram of material. And so the amount of water produced per day needs to be on the order of 10, 20, 30 liters per kilogram. Also, because obviously where it's arid and there's low humidity, you need the water most. The materials have to work well below typically what would be the lowest humidity you'd encounter, which is around 30%. Does 30% ever happen in the UK? Has it ever hit 30%? I doubt it. But there are parts of the world where you go outside and it's 35 Celsius, but it feels great, right? And they have to have certain performance features to become a regeneration optimized sorbent. Practically what that means is that they need what's called an isotherm, where you have a stepped isotherm where the water suddenly loads the pores at very low humidity. It's called a type 5 isotherm. They're known, but they're only known for high humidity, or they were only known to work at high humidity in mesoporous materials. So we had this nice little project where a small startup company funded us to go sorbent searching. I don't want to call it screening, but kind of was. And we got a fair chunk of money to have an 18-month to 2-year run at water sorbent desiccant screening. And I had some very sharp tools in my group. Dan and Andre love PCAM and were able to do the kinetics measurements, which is normally ignored, but in fact is critical to productivity. If you're cycling the material, the faster you cycle it, the more productivity you get out of the material. And they discovered that what you might think would be the way to go, load it, empty, is by no means the most productive way to capture water. In fact, what they do, it's called non-equilibrium cycling, where you just go back and forth around the mid-loading point of the sorbent. And when they finally learned how to properly collect kinetics data, which took quite a while, they were off to the races, because then you could calculate these heat maps. And the darker, the deeper the color, the more purple the color, the stronger the performance. And the optimal performance was less than 5 minutes loading and unloading. So this was one of those sorbents. So we actually succeeded beyond expectations in less than 24 months. In my group, we did the basic screening and testing and formulation and recipes for manufacture. The company Molecule did the machine design and the scale-up and the manufacture of the material that was used in the sorbent, which is basically a specialized paper. It's a cellulose composite of the sorbent, and at around 50-50 by mass. And that is exactly how building dehumidification is done, by the way, but it's white because silica gel is used in industrial and large building dehumidification. So we went all the way from TRL 1 to TRL 7 in 24 months. I'm going to finish off by going back to Barra. Since before my days as an undergrad, Barra, as I said, was the father of modern zeolite, synthetic zeolite chemistry. But he also studied molecular compounds and studied their absorption properties and published on them. And one of those papers is particularly relevant to what I've been talking about. It was a Werner complex, and he studied what happens when you expose this non-porous molecular compound to gases and vapors. And what he saw was they took up gas and vapor. They converted to a new structure. And in one particular case, those stepped isotherms that are so desirable were present. This is xenon, by the way. So what's happening here is that you're inducing a structural change, and you're capturing that gas or vapor by a non-porous solid. It's totally counterintuitive. This paper has hardly been cited. Nobody's really been following this area until quite recently. But the stepped isotherm now is a different reason. It was pore filling before. Now it's host gas complexation and structural change, dynamic solids. In the MOF area, it turns out that for the last 20 years, we've been discovering by accident breathing materials, materials that switch between closed and fully loaded phases. That the gas absorption is coincident or concomitant with a dramatic structural change. This is a 1995 Nature paper from Jeff Long's group, a simple MOF called cobalt BDP. This is a paper from my group. Our first publication in this area was in 2018, about the time I was here previously, and showed a very similar effect, but from a very different chemical composition and topology. This was a DIA network. And guess what? I came up with X before Elon Musk, but I'm not going to post on it. We call them XDIA networks because they're extended ligands. So we like X ligands in our group because they enable this process. So I still find this hard to believe, that a crystal can change that dramatically upon exposure to the right guest. But there are more naysayers than believers. And belief is not a good thing in science, right? Except you need to believe in what you're doing, but you don't say it in a paper, I believe that this is what our results mean, because you've got to have some evidence. And nobody was buying that these materials could be good for anything. They're interesting, they're curious, they're odd, but what can they do? And here are the reasons that people said they're not going to work, right? Well, you've got a structural change. It's going to take too long. It's going to take forever for a crystal to completely change its structure. Also, all that mechanical stress means they're going to break apart. They're not going to survive this dynamic process with large volume changes. Well, my student Gemma debunked that one last year in an RSC journal, J Materials Chem A, where she showed that another one of these XDIA networks not only did the change, it did it for water. So we actually got a water sorbent, the first flexible water sorbent that meets all the criteria for performance, below 30% RH. And there's the X ligand, by the way. So it's a long, thin ligand. Well, they're not going to be any good for separations because when you open up the structure, everything is going to go inside it because you have too much space. Well, we debunked that. This is my student Mohana, who studied a narrow pore material for acetylene and found that the material shrunk for acetylene using an induced fit binding mechanism. And it set a new world record for binding of acetylene by any sorbent. It's the new record holder for acetylene capture. Just earlier this year, we published a paper on ethane-ethylene, which is a very hard separation, where we set a new world record for selectivity for ethane over ethylene. Once again, because of a breathing structure which opened up and had induced fit. They're going to be a challenge to design, characterize a model. Well, they kind of are harder to characterize, but we're crystal engineers, right? We know how to fine-tune things. We know how to fine-tune composition. And my student Kyriaki was able to show that slight changes in ligand lead to very big effects on the sorption properties, in this case, CO2. And last, well, it's going to be hard to find the parents. You see, crystal engineering needs a parent. You need a generation 1 material. But guess what? There are 125,000 of them out there. They're already waiting there for us to just go back and look at them. We don't need new exotic materials. We just need to properly go back and look at the simple ones that are already out there. So to finish off, maybe slightly maybe more optimistic than I started. I think the next generation is going to be functional, flexible sorbents. And that they'll do all kinds of cool stuff that couldn't be done before. We're back to the doing different things. What are those different things? Trace removal of impurities, which is harder than bulk impurities, chiral separations, sensing of a particular gas or vapor at a very low level, water purification of various types, direct air capture of CO2. In terms of storage, there's adsorbed natural gas, hydrogen storage, medical applications of gas storage, such as nitric oxide and O2. And by the way, there's a big storage advantage. Not only can they have higher capacities, they have better heat transfer because they counteract the heat release during sorption. And last, and I said it's really not least, if you can do AWH anywhere, then you'll be able to make pure water on demand anywhere on the planet and dramatically reduce the costs of dehumidification. What is the key to functional flexible sorbents? Well, it turns out I hadn't opened up a biochemistry textbook in 50 years since I was an undergrad. And I remembered the lock and key mechanism, right? The lock and key mechanism is how enzymes recognize their substrates. Little did I know, no, there's no more lock and key. The chances you'll get a perfect fit lock and key are close to zero, right? What happens is that enzymes adapt to the substrate. You get an induced fit binding mechanism. That's how nature figured out how to do these very difficult trace captures. So if you can design your materials to do this, you can far exceed what we've already achieved in terms of properties over the last 10 years. And so that suddenly gives us a path to sustainability. And I don't know if anybody's curious about that first slide, what we're trying to show here. We're trying to show a sorbent capturing CO2 and water and feeding it to plants to grow them, right? Exactly what nature does, but from air, right? No water, CO2 from air, water from air. In fact, air will be the primary resource. Once we can design these sorbents, and once we have the will to start moving away from non-sustainable energy sources and chemical sources to sustainable sources, because they will give us pure water everywhere, food from air, fuel from air, and chemicals from air. And you don't have to imagine it, it's already in the movies, right? Okay, thank you again, Mike, especially for organizing, but you also for being here on a Wednesday evening. I'd like to acknowledge my group as very diverse in culture and geography. We have flags from all over the world, and we're very balanced on gender. Also, we have collaborators all around the world in Europe, North America, and China, and South Africa. And thanking you again. The west coast of Ireland is a great place to be, and it's a beautiful part of the world, so I feel very fortunate to have ended up there, but I've also been very well supported by government agencies and by industry for this work. So I would certainly be happy to entertain any questions or comments that you might have.
Brilliant. Thanks, Mike. That is a really great talk. We used to think of crystals as pretty decorative things, but it's pretty obvious that they are far more useful than originally thought. And also, the control and design of crystals has been beyond anybody's until now. So thank you very much.
Thank you. I'm not the only person in this field, but it has been an exciting field that's developed very rapidly, even since 2018, right? Because the properties, we now have the properties that are practically relevant that we didn't have before.
Brilliant. Chris, questions from the this group? Yeah, go for it.
Hi, thank you for the great presentation. I was wondering, I was thinking about the flexible modes. Do you see a future for them to be used as drug delivery devices? Because following up of that, can they be folded with a pH rather than?
Well, it's called stimulus induced. So anything that breathes needs a stimulus. And that stimulus can be lots of. We're focused upon pressure. It's really gas. When I say pressure, I mean it's a gas-induced transformation. But light, magnetism, pH, all of these things could be used, but you'd have to design it. And drug delivery, you'd have to have a convincing reason that you want to use a porous material. There are a guy.
No.
So in principle, you're only, as long as the chemistry is logical, yes, it has to be real chemistry.
How is the industrialisation being put into action? I mean, how does it relate to the existing method? Government's about to invest in.
Well, this is a road. So right now, suddenly there are carbon capture companies, startup companies coming up. The US, in particular, has 2 billion was committed. I think the UK just says they but you know I get to speak to these. So they're trying to take old technology and somehow slightly improve. That's what's going on right now. So they're looking for iterative improvements, not revolution. Because revolution requires a clean board and new engineering stuff. And liquid amines and amine grafted materials is 100-year-old, and they're trying to improve. Now, after saying that, there are 1 or 2 or 3 companies out there, and I've used the word love an awful lot. I love Steve James. But he's got a company called Porous Liquid Technology. And he is trying to use slurries, absorbents in liquids, and seemingly having a lot of success with energy footprint. So it needs revolution. And if I want to go back to my Dr. Doom, I'm not sure capitalism is well suited to this time. You need investment, you need will, and you need good government. So that's 2 strikes. And they need a stable geopolitical system all over. We're not focused on the way we should. I think it's doable. I'm an optimist, but it's doable in 5 years. There could be large-scale deployment if it's done like the space, where it's serious government, industry, academic developing materials and processes. And China might be the place. There's a lot more action. There's a lot more action than there was 2 years ago. So there's suddenly people are looking at an angle to get a new. They'd love to have a revolution, but you have to be a material scientist. You've got to come up with a system.
Go back, Lucy, go on the voice. A lot of the talk has been about gas capture from air, but hypothetically, the same concept of engineering, capture metal from steel. The application I would have in mind is uranium, billions of tons of uranium. Scale up.
There are review articles on that stuff. For gold and uranium, mining from seawater. So it's basically taking the porous material and having a chelate that can capture something very, very part per billion concentration. And my former colleague, Martian Ching, is now doing that. He's the one who's written review articles. And he has DOE funding. So yeah, that is another thing that's underway. So 6 years ago, it's okay, but it's crazy, but now it's actually there are real examples. And then you can go down the list of liquids. Capturing it, if you said there might be bad stuff in red wine, well, let's find a way to get it out, right? Make it even better. Leave it good. Good luck, Philip. It's coming back to if you really want to engineer let's break it down. You tell performance has to be energetically favorable operation up without defining it, then they can give you open to your range. Well, fortunately, I had a few companies listed on my side. A molecule company was an engineer who was working with. Well, the reason we went from 0, 1 to 7 in 24 months was we had an engineer visiting us once and discussing with us. And yes, so we were. They didn't have a. Well, they did have a process in mind. It was the same process. But working in a much milder condition, much milder. They gave us got to work at this humidity, it's got to have this level of productivity, it's got to have release at 50 or 60 degrees, which is kind of waste. So because of him, we set the bar up there. We actually had free process. That's CO2 that are people doing. We've worked with the CO2 who are nameless because they don't want to even admit that they were working in companies. And it was a similar issue, but they had a very different process. So we had to optimize the material for them. Yes, without the engineers, the real engineers. I'm not a real engineer. I'm a crystal engineer. Don't confuse me with real engineer. Or I might get arrested for falsely pretending to be an engineer. I'm a Royal College of Science graduate, not a City and Guilds graduate. So yes, I think we need that engagement. Look at this.
Thanks for your lovely talk. And thanks for your very what you're not supposed to get. I'll ask for more. Let's assume that with more than 100,000 trucks, there is nothing. Am I better off to go and engineering principles to make that general material? So do we have to do, or do you think we are still at the point where we need to random materials that they have and one product?
So by the way, I don't know if you know, but this is Pressure. He's with College London very well. Somebody I've run into more than once. He was an external for one of my students. But he knows more than he's letting on. So here's the basic. AI is not as smart and creative, at least yet. We have trouble spotting patterns. We tend to be derivative. AI is even worse. AI seems to dig itself tunnels, rabbit holes, and never climb out of it. How do you find the first member of a whole new class? And the answer is you only look for narrow core material. That's what we do. We're searching for simple, narrow core material. Now, it sounds, that's the truth. It's modeling contact, AI contact. Nobody even collected any data. And nobody was looking for narrow core material. So some of the people in my group have learned that lesson and said, I'm going to do that. And now they're getting mixed. there's a deluge of this going on. So my answer would be, I think a lot of the most simple, basic marks have already been done. But most of them have not been studied. Either they were non-porous or they were too narrow pores to give input. And that original copper BBC mark, second porous mark, was out in Jack's a month ago, which everyone's doing. So he's doing that. Go to the simplest, cheapest, easiest to make, longest known materials and reinvestigate them is the way I'm going. And if we fail, then I don't know. But I think I'm not so optimistic we can create all new classes of moss, because I think they've already, it's like organic chemistry. Yeah, there are new things to discover. The textbooks from when I was a student, not that different from the textbooks today. The design rules are already there. All of the simplest, cheapest, most readily available ligands have already been. So I should have said yes or no. I'm saying me.
I think we should go to our online quiz. And we'll go to Steve. But before that, we have a larger, a much greater online audience. I'd like to say greetings to Yamal Khan, who is the furthest participant that I know. So greetings, Yamal. But now over to Steve, the online.
Thank you very much. So, question from Jasbir Lota. Very interesting talk. As a secondary school teacher, how do you suggest getting young people interested in the world of the wonder of crystals?
Well, the Royal Society of Chemistry should be part of that. But also there's the International Union for Crystallography. So that's not a three-letter acronym. It's IUCR. Has actually a manual for high school teachers to teach students about growing crystals. It's a handbook. There's a 2002 edition floating around, and my email is on. I'd be happy to forward it, but it's written specifically for teachers to use with students, and it's things like borax, crystallizing borax. It gives you recipes, and you can have a crystal growing competition between your students to see who gets the prize for the best looking crystal, and the teacher can decide that.
Online question we had.
Okay, another one.
We destroy that to let test crystal known in nature white. So much inappropriate use of when I London, the green spice theory or concrete. This not ever we must stop using inappropriate.
100% agree.
And thank you for your lecture. Very good.
I have a terrible carbon footprint, and I justify it that I can convince one or two young people to go in this area, solve a problem, it pays. So I'm happy if I can get one believer from every lecture. And, saying something that's wrong with the way people are afraid. We could. Of course, Brazil went away from, you probably know in Brazil, during one of the oil crises, they had real problems with supply shortages, so they said, we're going to make it all bio. And now they balance, in Brazil, every gas station has petrol or bioethanol, which one do you prefer? Each car you can flick back and forth. And it's the price. They base it upon consumer price, but it's not eliminated. what worries me is if we stopped increasing emissions, we still got 3.4 people. It needs much more than just flatten. It needs to go down to net zero. And it's not only is it not happening, it's not possible. And the effects, I think, are now becoming, I hope I'm wrong, but certainly looking like we're hitting a tip. Climate patterns have changed much for the worse in parts of the world that we all know.
If we don't change our behaviour, we're sorry to say that.
Well, it's hard to imagine we'll cope well with global climate crisis, when, given the politics that we're seeing right now.
One more.
He's saying about I like always have fascinating. But I've been on a project
A better blue.
yes.
Russian.
I've got a sample of partial fluid stick. I use it.
It's got cyanide in it. Too.
Oh, yeah.
So it's not abstract.
Anyway, with the team who developed why is it why in lower concentration
Well, I definitely can't answer that question. But what I can tell you is that chemists can do that. So chemists can control composition incredibly well. And then you can do systematic structure analysis. So that color can be fine-tuned. Chemists can know how to control the precise composition.
earlier.
Right. Once you have the key is the same in synthetic chemistry as molecules as with material. Once you have a parent, we know how to treat it. Chemists are good cooks. I heard that. I was at a meeting and you cook. Yeah. We all cook.
It's the same.
Synthetic chemistry.
It's a.
And we don't follow recipes.
Oh yeah, it's probably.
We'll stop at that point. We've now got a network meeting with juice, wine, coffee. There'll be further questions that crop up. So please ask Mike there during the network meeting, because Mike's not allowed to go away. And thank you very much all for attending.